Thank you for the introduction to the workshop. Thank you for the invitation and welcome to my talk. So this talk is titled Euclidean Distance Degree and Mixed Volume, and it's a collaboration with Frank Sottile and James Woodcock, both from Texas A&M University. And the title of my talk has two subjects. Euclidean distance degree is the first and mixed volume is the second. And so in the beginning of my talk, I would like to discuss what these two terms mean, or what happens with these two subjects. Okay. So I will start with Euclidean distance degree. What is this? So here's the setting. Consider an algebraic hypersurface X. So X is given as the vanishing of a single polynomial in R to the n, so it's a real algebraic hypersurface, and the point U in R to the n. So for instance, X could be this blue curve here in R2, and U could be this red point. So this example is this example here. And then you consider the following problem. You consider the problem of computing the critical points of the square distance function, the function from the hypersurface to U. Okay, so this is the square distance of the hypersurface to U, and you want to understand what are the critical points of this function. Okay, so where does this function have a local minimum or local maximum or saddle point? So for instance, here you see again my blue curve, you see a red point U, and then you see a couple of points on V, and these are the critical points of the distance function. And here you see the global minimizer for this distance function. So this point is the closest point to U on the hypersurface. Okay. And the way to compute these critical points is by solving the associated Lagrange multiplier equations. This is a system of polynomial equation which looks like this. So I call this LFU, and it has variables x and one additional variable lambda. And the equations are first f of x, okay, so x needs to be on the hypersurface. And then the second condition is that the gradient of f at this point is parallel to x minus u, and this is just the derivative of this function, okay? So that's the Lagrange multiplier equations for this particular problem. And solving these equations solves this problem of computing the critical points. And observe that by solving these equations, you can find the global minimum of this of the distance function from V from the hypersurface to U. But you can also find one point on each connected component, right? Because each connected component contributes at least one local minimum to this distance function. So you get 1 point on each connected component, which is of course important if you want to, for instance, learn the topology of a hypersurface. Sorry about that. Sorry. Okay, so these are ED critical points. And then the Euclidean distance degree is the number of complex solutions of the Lagrange multiplier equations. Okay, so this is a system of polynomial equations. You count the number of complex solutions, so number of zeros over complex numbers. This is what is called the Euclidean distance degree of this hypersurface. Okay, so here in my example, you can see 8 real critical points, but the example is actually ED degree 36, so there are 28 complex solutions to the system of equations. So you can think of Euclidean distance degree as some sort of measure of complexity for solving these Lagrange multiplier equations. Okay, that was the first part. Now the second part is about mixed volume. So for the moment, let's switch gears completely and look at a new subject. But both of the subjects, they will come together later in the talk. So mixed volume. Mixed volume, in this part of the talk, we are considering sparse polynomials. So g of x is a sparse polynomial in n variables. If it looks like this, so if g of x is given as a linear combination of monomials indexed by some subset of z to the n, okay? And this does not need to be the subset indexing all monomials. It can be a small subset. So this is why this is defined as a sparse polynomial, okay? And this indexing subset A is called the support of G. Okay, so here's an example. I plotted a support in Z to the 2, so this is a bit tilted into the plane. And you can see there's the point 0, 0, 0, 1, 1, 1, 2, 1, and so on. And this gives you the following polynomial. So here's the coefficient which corresponds to this point, and so on and so on. Okay, so this is an example of such a sparse polynomial. And as you can see, this is a polynomial of degree 3, but they are not all terms of degree 3. So there are less terms. This is why this is a sparse polynomial. Okay. Mixed volume. So now I consider a system of n sparse polynomial in n variables. So let me call this G. So G consists of G1 through Gn. It's a system of n sparse polynomials. And each of the Gi's has a support AI, okay, which indexes the monomials that appear in Gi. And then I define Pi to be the convex hull of Ai in Z to the n. Okay, remember Ai was a set of points in Z to the n. I take the convex hull, gives me a polytope which is called the Newton polytope of Gi. Okay, that's a convex polytope in R to the n. And then I define the mixed volume of my polynomial system G. I define it to be the mixed volume from convex geometry, the mixed volume of P1 through to Pn. Okay, so I have n polytopes in R to the n. To this I can associate the mixed volume from convex geometry and then define this to be the mixed volume of the system G. Now here's again an example. This is basically the example that I had before, just that now I also plotted the convex hull of the points that I had on the previous slide. Okay, so this would be the associated Newton polytope for the example from the previous slide. Now here's the famous BKK theorem, and it's a fantastic theorem. If you don't know it, you should know it by now, and you should really appreciate it. It's fantastic, and it says the following. So let G be a system of n sparse polynomials in n variables, like before. And then we assume that g of x equals to 0 has finitely many solutions. Okay? Then the number of solutions over the complex torus, and by this I mean all solutions where none of the entries is equal to 0, so where all of the entries of the solutions are some complex number which is not 0. The number of solutions over this set is bounded by the mixed volume of G, which was the mixed volume of the associated Newton polytopes. And equality holds if G of x is general. So I will explain what general means very precisely, but just think of this, if the coefficients of G of x are some sort of randomly chosen, then this is an equality actually. So you can compute the number of zeros as a mixed volume of something, mixed volume of Newton polytopes. So here's the research question that motivated this work, and that is also the part of this, the content of this talk. The question is, if you look at the system of equations that are the Lagrange multipliers, is it general? Okay, is it general in the sense of BKK theorem that I just explained? So is the number of solutions of this system of equations equal to a mixed volume? And we cannot just say that, okay, a general polynomial system has equal to mixed volume many solutions. We cannot apply this sort of generality here because this system of equations is really structured. So the first entry is f of x, and of course, all the other entries, they depend on f because it involves derivatives of f. Okay, so there's a very structured system. It's not clear if the BKK theorem, the general of the BKK theorem applies here. So that's the question. So what is a general polynomial system in this sense? What does this mean? So now let's dive a little deeper into the subject of BKK theorem. So let's take W and R to the n, and let's take again a support set in Z to the n, and then I call HW of A, I call this the minimum value of the linear function that W imposes on A. Okay, so I call the minimum value of W transpose A over A, I call this HW. And then AW, I call the points in A which attain this minimum. And this is the face of A exposed by W. So it's actually not the face of A, but the face of the Newton polytope of A, but okay. I hope you forgive me this impreciseness. Now, if I take G to be a sparse polynomial, I call GW the polynomial that I get from G by just keeping the monomials corresponding to this face exposed by W. Okay, so I just delete all the other terms that do not belong to the face. So for instance, here I have back my example from the beginning. Now we have W equals to 0 minus 1. So this is an arrow which goes in this direction. And you see the face of the polytope is exactly the face on which this arrow points. Okay, so that's W here. And this is the face containing of these 3 points. So that's AW here. And then GW would be the polynomial that corresponds to these 3 terms, which you can see at the bottom of the slide. So recall that I call G subscript W the polynomial which I obtain by just keeping the points, the terms corresponding to the face AW. And then here's the theorem by Bernstein, which very precisely says when a polynomial system is general. And it says this: the number of solutions of G, so this is again my system of sparse polynomials, G1 through Gn, in the complex torus equals the mixed volume of G if and only if for every non-zero W, the facial system being made up of G1 of W and so on, and Gn of W, so these are these guys up here, if these so-called facial systems have no solutions in the complex torus. So here's a certificate, if you want, a way to prove that a system is general just by showing that these particular systems, they don't have any solutions. If you can show that, then you know the system is general in the sense of BKK theorem. And we would like to call these kind of systems Bernstein general, just because of this theorem here. Okay. So now let me combine the 2 parts that I just discussed. So the first one on Euclidean distance degree, the second one on mixed volume. And I claim that Euclidean distance degree equals mixed volume. So this is here. Euclidean distance degree equals mixed volume. So recall the Lagrange multiplier equations. These are this is this set of equations for this hypersurface. And then if this hypersurface is not contained in the coordinate hyperplane, and if the point U is sort of general, then we can show that all of these solutions of this polynomial system, of this Lagrange multiplier equations, they're all contained in the complex torus. And the reason for this is some dimensionality argument, so not very sophisticated. But what this shows is that the ED degree of this hypersurface, which is defined as the number of complex solutions, is bounded by the mixed volume because all the complex solutions are actually solutions in the torus. So we have this. This we get for free, essentially. But then we have this theorem that we proved, so my co-authors and I, that if f is a general sparse polynomial with support A, and we need to assume that the origin is in A. If this is the case, then the Lagrange multiplier polynomials for this general polynomial are Bernstein general, which implies that the ED degree of this hypersurface is equal to the mixed volume. Okay, so we show that an Euclidean distance degree of a hypersurface equal to a mixed volume of the Newton polytopes of the Lagrange multiplier equations. So this is the content of this theorem. Let me give you a visual break here. So if there are questions at this point.
Hi, Paul, I have a question.
Yep.
Do you guys know what the generality conditions on U are?
On U? No, we don't.
Okay, thanks.
One can work it out probably, but we didn't do that. Okay, thanks. Okay, so now is the time to digest all of this. So Euclidean distance degree is a mixed volume, usually. That's what this theorem is saying, at least for hypersurfaces.
Okay. Does Bernstein theorem act as the upper bound for the solution for the system of polynomial equations?
Sorry, I did not understand that.
Is it like upper bound for the solution for the system of polynomial equations?
Yeah, that's exactly what it is. Okay, let's keep going. So this is the theorem. And the way to prove it is, of course, take this certificate by the theorem of Bernstein and show it for this particular system of equations, right? That's the proof strategy. We take Bernstein theorem, which says, take all the facial systems, check for solutions of the facial system. If there are no solutions, then you have proven the theorem. That's the proof strategy. And here's an example to show you how that proof could work. So let me again take my example from the beginning. It's this Newton polytope here. So this is F, and it has this Newton polytope. Then the Lagrange multiply equations associated to this polynomial here, they look like this. So here's F, which corresponds to this Newton polytope, and then here are the two other entries. So it's the derivative of F with respect to x1 minus lambda u1 minus x1, and the same for x2. And now what are the Newton polytopes for the Lagrange multiply equations? So they look like this, because in Lagrange multiply equation, we have this additional variable lambda. So here I have x1, x2, and then in the third dimension, I have lambda direction, okay? And then this is the Newton polytope for the derivative of f with respect to x1 minus lambda u1 minus x1. So you get this additional piece up here, and then you take this polytope, and then the same for x2. So this triangle down here is the Newton polytope of the derivative of f with respect to x1, and then you add this piece up here, and this line here is the derivative of f with respect to x2, and you add this line here. So if you look at this polytope, taking derivative, let's say for instance, with respect to x1, just shifts the whole thing in this direction. So it cuts off here, and then this is what remains. So this would give you derivative with respect to x1, for instance. Okay, so that's how you get those other polytopes. And then you need to show that none of the facial systems corresponding to these three polytopes has a solution. Okay, so for instance, you could take w equals to 0, 1, 0. Now let's look back at our three polytopes. So the 0, 1, 0, it goes in this direction. So this one cuts out this here, and here it cuts out the red triangles on the bottom. And these three red faces, they give you this this facial system for the Lagrange multiply equations. And what you observe here is that this system of equations depends on x1 and lambda, but not on x2. So, and this is what happens. This is what happens all the time in these kind of examples. So we have three equations, we have two variables, and one can show that in general there's no solution. There's no solution at all, so there's no solution in the complex torus, because three equations, two variables. Okay, so that's one example of the proof strategy. And this example demonstrates one part of our proof, and there are other parts. So there are exactly three parts, but I wanted to show to you one of them. And for time reasons, I'm skipping the other two. But this example demonstrates one piece of our proof for showing that Euclidean distance degree is equal to mixed volume. Okay. And this, so this proof then rests on the fact that you get a system of equations with less variables than equations. Okay, so why is our theorem interesting? Part one. So this theorem is interesting because it's interesting mathematics. Okay, but there are also other parts of the story why this theorem could be interesting for you and for your research in algebraic geometry and machine learning. And here's the first reason. So there are two parts. Here's the first part. The first part is that with our theorem, you can now compute Euclidean distance degrees by using tools from convex geometry, because remember, we proved that Euclidean distance degree is equal to mixed volume. Now this mixed volume is a concept from convex geometry. So you can use tools from convex geometry for computing it. So for instance, what we can show is the following. So let A be a vector consisting of numbers a1 to an, and let ek of a be the kth elementary symmetric polynomial in n variables evaluated at a. So it's this expression here. Now take f to be a general polynomial with Newton polytope, which is this here, b of a, and it's just a box. Okay, so it's a box and r to the n. So this is sort of yeah. In 2 dimensions, it would be a rectangle. Okay, in 3 dimensions, it would be a cube, and so on and so on. So if your polynomial defining a hypersurface has this Newton polytope and is sufficiently general, Then we can compute the Euclidean distance degree of the hypersurface, and it is this expression. So it's the sum of k from 1 to n of k factorial times the kth elementary symmetric polynomial evaluated at a. And a index is the length of the box. Okay. So here's a new formula for Euclidean distance degrees, which has not been there before, which you can now compute by using our theorem. So that is one reason why our theorem is interesting. So here's a second reason why our theorem is interesting. Why is our theorem interesting? Part 2. And this is I think, the part which is even more interesting. So at least in my opinion. Okay, others might see it different, but this is my opinion. So in this part is about polynomial homotopy continuation. So again, let g of x be a system of n sparse polynomials in n variables. And then for solving the equation g of x equals to 0, there's an algorithmic framework which is called polynomial homotopy continuation. And the idea in this is the following. So for solving g of x equals to 0, you take another system, g start. Let me just call it g start because it's usually called the start system. And g start must have the property that you can compute or easily compute its zeros. Okay, so it's a polynomial system where you know the zeros or where you can easily compute them by solving some easy auxiliary problems. Then you connect g start and g with homotopy. So that's just a path in the space of polynomial that connects g start and g. So that at time equals to 1, you are at g start, and at time equals to 0, you are at g. And then you track the zeros of g start, which you know, or which you can easily compute, from t equals to 1 to t equals to 0 along this homotopy that you just defined. And when I say tracking, it means what you actually do is you are solving an ordinary differential equation, which is this equation. So the initial values are the solutions of g start, and then you use this ODE. You use standard numerical methods in solving ODEs for solving this polynomial system. So that's what is called polynomial homotopy continuation, and it's a very well working concept and also implemented software, which has found a wide range of applications. So this is polynomial homotopy continuation. Now, what has this to do with my talk is the following. So there's something which is called polyhedral homotopy, and that's a specific homotopy given by two authors, Huber and Sturmfeld. So I think Ben Sturmfeld is in the audience here. You can give more insights if you want. But what they do is that they provide a specific start system for polynomial homotopy continuation and a homotopy that has the following properties. So first of all, G start, the start system, has mixed volume of G many isolated solutions, and those solutions can be easily computed. And secondly, you get a homotopy which for all t between 0 and 1, except for t at 0, because there you don't know what's happening, but for all of the other t's, you know that the system h, x of t, so your homotopy, has also mixed volume of g isolated solutions. Okay, so that's a that's polyhedral homotopy. So in our setting, what this means, if now G is the system of Lagrange multiply equations, we also know that at t equals to 0, at the point where, at the polynomial system where we're interested in, it also has mixed volume many solutions. That's the theorem that I just discussed, right? So it means that this polyhedral homotopy tracks an optimal number of starting solutions. It tracks an optimal number of paths, right? Because the start system has as many solutions, namely mixed volume, many, as the system we're interested in. So if you start at G start, none of the solutions which you will track will be wasted. You will not track too many. You will track the exact right amount of paths that you need to do. So polyhedral homotopy is implemented in a few softwares. So notably homotopycontinuation.jl. So that's the software where I'm partly involved in. Then there's PHCPAC and Hom4PS. So I think those are the most prominent ones at the moment. They all have this strategy implemented. And our theorem implies that polyhedral homotopy is optimal in the sense that I just discussed. Is optimal in the sense that you do not track too many paths. You track the exact right amount of paths that you need to do for computing complex critical points of the distance functions for this hypersurface. And that's now, I think, very interesting, coming back to learning, coming back to computation, because it shows that polyhedral homotopy is, in some sense, an optimal strategy for solving these equations, which in turn gives you an optimal strategy for minimizing the distance or for finding a point on each connected component on a variety. And I think that's a very interesting property or consequence of our theorem. And by the way, this is one of the few known instances where, of a structured problem at least, where we have such an optimal homotopy available. Usually when you do homotopy continuation, you start at a system, the start system has way many more solutions than the system you're interested in. And in the tracking procedure, you have to sort out many solutions. And this is usually a wasteful computation. So in this case, this is not so. In this case, polyhedral homotopy is optimal, which is, I think, fantastic news. Okay, thank you for your attention. This is all I wanted to say.
Shall we thank Paul? Oh, are there any questions?
I have
just
one.
unmute. Yeah, great.
Should I proceed first? Yeah. So Paul, thanks for the talk. If I understand, polyhedral homotopy will also track my singular solutions, or it will only track non-singular solutions? Polyhedral homotopy. It gives me complete solutions, that is singular and non-singular. What I mean singular solutions are solutions that are having multiplicity greater than 1.
Yeah, that's the point. It will do that.
It will give me singular solutions as well, polyhedral homotopy. It
will give you also singular solutions, but you need to do some more additional stuff to get them, some sort of end game. But this is not the point here, because we are talking here about general polynomials with a given support, and these are usually, they don't have singularities, and that's the point.
Okay. Okay. Thank you.
Okay, I think George, were you next?
Yeah, I just wanted to ask, what is a, so you talk about optimal solution. Can you just describe a little bit more of like what happens when it's not optimal, and why, why do we care that it's optimal?
Yeah, so okay, so I, on my daily in my average day, I solve a lot of polynomial systems with this technique, homotopy continuation. And if you have a structured system and you know nothing about it, you're just trying to solve it, you have to come up with some start system. And there are some general rules for constructing start system. One of them is, for instance, polyhedral, but there are other strategies. But usually what happens in structured problems is that your problem has few solutions, but the corresponding start system that your algorithm constructs has many solutions. So, okay, just to give you an idea, I solved one system of equations the other day, which had about, I don't know, 600 solutions, but the start system had something like 100,000. Okay, so this means when you track your solutions along the way from your start to your target, you have to sort out all the solutions which are not the 600 ones that you're actually interested in. So you have to sort out 100,000 minus 600 solutions in the way, which, okay, you can do it, but remember that until the point you know when to sort out, you might have already computed a lot of things by just tracking 100,000 solutions. That's a wasteful computation. So what this theorem says here is that if you want to solve Lagrange multiply equations for EDD, this is not happening. It says that the polyhedral homotopy starts with the optimal number of solutions. There's no solution that needs to be sorted out. Okay, that's what I mean when I say optimal. And because in homotopy continuation, which usually takes a lot of computation time, is sorting out these fake solutions that are not really solutions. That's usually the most wasteful computation.
I see. Thanks.
Great. And Carrie, your question?
Thank you for the nice talk, Paul. My question is, have you thought whether similar results can be obtained for the maximum likelihood degree?
So yes, thank you for that question. So not for the ML degree, but probably it can. But what I was thinking about other types of equation that have structure, if one can show something like that. So I have not thought about the actual proof, but I did some experiments on the computer, and there are some other sets of equations which seem to behave like that, that the number of solutions can be expressed as some mixed volume. So something which I would like to do next is not, okay, and it's not ML degree, but is number of eigenvalues of tensors. So I think this story can also be written for eigenvalues of tensors, sparse tensors. But ML degree would also be interesting, but I just didn't think about it yet.
Thank you.
Okay, wonderful. Any more questions? Okay, there's nothing in the chat. Let me just have a look. No. Well, in that case, shall we thank Paul for his wonderful talk again?